So hello students, welcome you all. Welcome to this YouTube channel. So here we have to discuss the differential protection. So the differential protection, the main application is to have a zone of protection, right? Is to have a zone of protection. So here this is a lengthy transmission line that we have to protect using the differential protection, right? So I have chosen a section of transmission line AB that I have to protect using differential protection, right? So this is the CT, 100/5 is the CT ratio. Here this is also 100/5 CT. This is the CT1 and this is the CT2, right? So this lengthy transmission line I have to protect using differential protection, right? So in this protected zone, if any fault occurs, then the relay must operate to trip the circuit breaker, right? So here you see this is the, I have connected the CT1 and CT2, and this is the operating coil. So if any current flows in the operating coil, then the relay will operate. If there is any current flow in this operating coil, then this relay will definitely operate, right? And if the difference of current in this operating coil is 0, then the operating force will be 0. So that means the relay will not operate, right? So if there is any faulty condition within the protected zone, then the difference of current will flow in this operating coil and then the relay will operate, right? So we have a lengthy transmission line, and on this let AB is declared as a zone of protection, which is to be protected using the differential protection scheme, right? So we have connected one CT at point A and another CT at point B, right? So the characteristics, what are the characteristics which are desired for the two CTs? Number one, both the CTs must have the same CT ratios. Number two, saturation level of both the CTs must be the same. These two conditions, these two are the characteristics, right, of the two CTs which are used for the differential protection scheme. If both the CTs do not have the same CT ratio, then it will lead to error. Similarly, if the saturation level of both the CTs is not the same, then also it will lead error, which is the practical case, that the two CTs of the same CT ratios must not have two CTs of the same CT ratios, they do not have the same saturation level practically, right? That we will see later. So the characteristics which are desired for the two CTs are: number one, both the CTs must have the same CT ratio, and number two, saturation level of both the CTs must be the same. So now, using a copper wire which is known as pilot wire, we have connected the secondaries of the two CTs, right? All right. Right. So here you see this using the pilot wire I have connected the secondaries of the two CTs, right? So now what is the principle? What is the principle of the differential protection? Just have a look at it. So condition 1, that is a normal operating condition, right? Let us take the normal operating condition. So in the normal operating condition, let the current everywhere is 100 ampere. Let the current everywhere is 100 ampere. In that case, the CT1 secondary current will be 5 ampere, right? As per the CT ratio. In the primary, if it is a 100 ampere current, then the CT secondary will give you 5 ampere as per the CT ratio that I have chosen 100 by 5, right? Similarly, CT2 secondary current is 5 ampere, right? Now tell me, what is the difference of current in the operating coil? See this, 5 minus 5, that is 0 ampere. You see here, the CT1 secondary current is 5 ampere, CT2 secondary current is again 5 ampere. So CT1 secondary current is 5 ampere and CT2 secondary current is 5 ampere. So what is the difference of current in CT, difference of current in operating coil? 5 ampere minus 5 ampere, that means 0 ampere. So that means in the normal operating condition, the difference of current in the operating coil will be 5 minus 5, that is 0. So that means relay will definitely not operate, and that's what we are expecting, that in the normal operating condition relay should not operate. So relay is not operating here, right? So the current in operating coil, that is the difference of current in operating coil, is 0. So the relay will not operate for the normal operating condition, because the operating force for 0 ampere current will be 0. Relay will not operate, right? So here, now let us take the condition number 2, that is the faulty condition. So in the faulty condition, that means when there is a fault that occurs externally, right, externally at point P1, right? So that means, let us say an external fault of having fault current of 1000 ampere occurs at point P1. See, this point is P1, which is external to the protected zone. Protected zone is AB only, right? This is A and this is B. So this is the protected zone or protected area, right? And outside this protected area, the fault occurs at point P1 having fault current of 1000 ampere. Then suppose out of 1000 ampere, you see this 1000 ampere is the fault current at point P1, that is external to the protected zone, right? So here the CT1 secondary current is 50 ampere, because the same fault current will flow through CT1, right? And the same fault current will flow through the CT2. Same fault current will flow through the CT1 and same fault current will flow through the CT2. So as per the CT ratio, CT1 secondary current will be 50 ampere and CT2 secondary current will again be 50 ampere, right? So CT1 secondary current is 50 ampere and CT2 secondary current is 50 ampere again, because both the CTs are seeing the same fault current. So the operating force is, so the operating coil current is 50 minus 50, that is 0 ampere, right? Both the CTs will see the same fault current because it is external fault, that is also known as through fault, right? So the difference of current in this relay operating coil in this case also will be 0, right? So 50 ampere minus 50 ampere will be 0 ampere. So the difference of current in the operating coil, in the relay operating coil is 0. So the relay operating force is 0. So relay will not operate. Relay will not operate for this through fault or external fault, right? Relay will not operate, right? And that is expected, that the relay should not operate for any fault which is external to this protected zone AB, right? And the relay should only operate when there is any fault within this protected zone AB. Then and only then the relay should operate, right? So we have seen the two cases. Number one case, that is a normal operating condition. The difference of current in this relay operating coil is 0, so the relay will not operate. Case number 2, for the external fault, right? For the external fault which is external to this protected zone AB, that is occurring at point P1, right? With fault current of, let us say, 1000 ampere, relay is not operating, because again the difference of current in this relay operating coil for this external fault P1, that is 50 ampere minus 50 ampere, 50 ampere minus 50 ampere, that is 50 ampere minus 50 ampere. The difference of current in this relay operating coil for the external fault or the through fault is 0. So the operating force is 0. So the relay will not operate, right, for this external fault, right, which is outside this protected zone AB. Now let us take the case number 3, condition number 3, right? So in this condition number 3, a fault at point P2 occurs, right? At point P2, which is inside this protected zone, occurs, right? So now let a fault occurs inside the protected zone AB. So in that case, let us suppose the fault current is 1000 ampere, right? So out of this 1000 ampere, 900 goes to the fault point P2 and 100 ampere goes to the load, right? So CT1 secondary current will be 45 ampere and CT2 secondary current will be 5 ampere as per the CT ratio. So the difference of current in the operating coil, difference of current in this operating coil is, it will be 45 minus 5, that means 40 ampere, right? So the difference of current in this operating coil will be 40 ampere, that is a non-zero value, unlike the earlier two cases, right? So operating coil current is not 0, so the operating force is not 0. So that means relay will definitely and definitely operate for a fault inside the zone AB. That's what is desired, that's what we needed, right? You see here what I said. I repeat once again. You see here what I said. In case number 3, let us say fault occur at point P2. This is a point P2, right? So here a fault occur. This point P2 is within the protected zone AB, so the relay should operate. That's what we desire, right? So suppose the fault current is 1000 ampere, right? So out of 1000 ampere, let us say 900 ampere goes to the ground and 100 ampere it goes to the load, right, through the CT2. So what is the current, what is the fault current which is shown by this which is seen by this CT1? Tell me, what is the current which is seen by this CT1? The current seen by the CT1 is 900 ampere, because I told you that let us suppose that a 900 ampere current goes to the ground. So the current seen by the CT1 is 900 ampere, right? And what is the current which is seen by the CT2? This is 1000 minus 900, that is 100 ampere. So the current which is seen by the CT2 is 100 ampere, right? Current seen by the CT1 is 900 ampere and the current seen by the CT2 is 100 ampere, right? So what is the CT1 secondary current? CT1 secondary current will be 45 ampere, right? Because the current seen by the CT1 primary is 900 ampere. So the CT1 secondary current is 45 ampere. And the current which is seen by the CT2 is 100 ampere only, because 900 ampere goes to the ground to the fault point, right? So the current which is seen by the CT2 is 100 ampere. So that means current seen by the CT2 primary is 100 ampere. So the CT2 secondary current is 5 ampere as per the CT ratio, which is 100 by 5. So the difference of current in the relay operating coil will be 45 minus 5, that is 40 ampere. So 40 ampere is non-zero value of current in the operating coil. So the operating coil current is not zero, that is 40 ampere, and that's why the operating force is not zero. So the operating coil current is not zero, operating force is not zero. So the relay will definitely operate for a fault which is inside this protected zone AB, right? So for the relay to operate, the difference of current in operating coil, it must not be zero. Have you understood my point? Have you understood this point? And relay will not operate if the difference of current in the operating coil is zero. And relay will definitely operate if the difference of current in this operating coil is not zero. Then the relay will definitely operate. So we have seen the three cases. In first case, in the normal operating condition, both the CT will see the same fault current. So that's why operating coil difference in current in operating coil is zero. Relay will not operate. In the second case, the fault occurs externally, that is through fault at point P1. So again both the CT will see the same fault current. So CT2 secondary, CT1 secondary and CT2 secondary current will be same. So again the difference of current in the relay operating coil will be zero. Again the relay will not operate for this external or through fault outside this protected zone. Again the relay will not operate. Now case number 3 that we have taken, it is fault which is internal to this protected zone AB. That means at point P2 a fault occurs with fault current of 1000 ampere. Out of 1000 ampere, 900 ampere suppose goes to the ground to the fault point and only 100 ampere goes to the load, right? So CT1 primary current seen by the CT1 primary is 900 ampere and CT2 primary current seen by the CT2 primary is 100 ampere. So that means CT1 secondary current is 45 ampere and CT2 secondary current is 5 ampere. So that means the relay operating coil difference in current in the relay operating coil will be 45 ampere minus 5 ampere is equal to 40 ampere. That means in this case now difference of current in the relay operating coil is not zero. That means operating force is not zero. So that means relay will definitely operate for this fault which is inside this protected zone AB, right? Suppose if it is a solid fault, had it been the solid fault, then whole 1000 ampere current will go to the ground. Then the current seen by the CT1 primary will be 1000 ampere and current seen by the CT2 primary current is 0 ampere. So CT1 secondary current by the CT ratio is 50 ampere and CT2 secondary current is 0 ampere. So in this case also difference of current is 50 ampere minus 0 ampere. That means again the difference of current in the relay operating coil is not zero, so relay will definitely operate, right? Have you understood? So the logic of differential protection is that if the fault occurs externally, then both the CTs will see the same fault current. So the difference of current in the relay operating coil is zero. That means relay will not operate, definitely not operate. But if the fault occurs inside the protected zone, then only one CT will see the fault current. So the difference of current in the relay operating coil is not zero. That means relay will definitely not operate, definitely operate. Relay will definitely operate because relay operating coil is not zero, because the difference of current in the relay operating coil is not zero. That's why relay will definitely operate for any fault which is inside the protected zone. That is the logic of differential protection, right? Now you see here the practical problem with this. There is one practical problem that we face in differential protection. What is that? The practical problem is that the two CTs can never be exactly identical. Their CT ratio can be same, but their saturation level will be different. That leads to the problem of ratio and phase error, right? So a differential relay may maloperate due to the unequal saturation level of the two CTs. To avoid this malfunction of ordinary differential relay is modified to percentage differential relay, right? And a differential relay using percentage differential relay is called as Merz-Price circulating current method. This is called Merz-Price circulating current scheme, right? Now, why unequal saturation level? What is the reason? Reason is that the reason of unequal saturation level is that the core of both the CTs will face the different temperature at different point on the transmission line, right? Reason of unequal saturation level is that core of both the CTs will face different temperature at different point on the transmission line. That's why the saturation levels are different, unequal, right? That's a practical problem that we encounter, right? So that concept of percentage differential protection, that is basically known as Merz-Price protection scheme, that we will discuss in the next video, right? So thank you very much. Thanks for watching. Subscribe to this channel if you like, right? Thank you very much.